Hello everyone, Namaskar, Saudi Club. Welcome you all to Membrane and Filtration Tech Talk. In this session today, we're addressing the topic on the bio-based membranes for carbon dioxide separation. And the presentation will be given by Dr. Rajashree Borgohain. So before I invite her to give a talk on this subject today, this is a program by TechnoBiz, Membrane Filtration Tech-Talk. Let me quickly explain to you what is all about TechnoBiz. TechnoBiz is a company based in Thailand, established in 2005. It is recognized as International Resource Center for Polymer Processing Industries and also the process and industry technologies. You can always find about TechnoBiz more information on it at technobiz.org. Feel free to check it out this website. We are pretty much global in terms of offering our services. Let me quickly give you an overview about what kind of services we offer. We are specialized in the professional education. We offer online training programs, in-person training programs. We have master classes, workshops. We also offer executive diploma program, 360 degrees. So this is basically a program which cover both on the technology and the management. Currently, we are offering for the rubber industry, but we will be having more in the future on membranes as well. We also do the skill assessment test. We have publications, and then we have the digital library. So these are various issues about the professional integration aspects of it. When it comes to the business services, we host international exhibitions and conferences. We also have virtual events like today, webinars. We host road shows, networking events. We do have the technical and the business consulting, and we do factory and process audits on various processes. And finally, we do the marketing and branding of the technologies and products. So this is a broader spectrum of the services that we offer in terms of professional education and also the business services. What we cover, we are not offering our services to everything, every technology. We are specialized in few areas only. One is on the polymer side, on the rubber, latex and tire, plastics and composites, polyurethane foams, adhesives and coatings. And on the non-polymer side, more into the energy, environment, membranes and filtration, recycling and recovery. There is some overlap on this thing, but it's more about the other specific areas of our industry and technology segments. We also focus on the nanotechnology, smart manufacturing, and also various chemical processes. So this is what our focus, what kind of services we offer for the industry. And again, please do check our website, technobiz.org, for more information on the TechnoBiz. So that's about it. And if you have any questions on the TechnoBiz and its services, please do write to me. I'm happy to assist you. So let's get into today's session on the bio-based membranes for carbon dioxide separation by Dr. Rajashree Borgohain. She is a PhD. She already completed a PhD in chemical engineering from the Indian Institute of Technology, Guwahati. Her main area of research is membrane-based separation. She has published several papers in various international journals. Her PhD thesis has been awarded the best thesis in chemical engineering research by Indian Institute of Chemical Engineers and also by the IIT, Indian Institute of Technology, Guwahati as well. Currently, she is serving as a reviewer for several journals of the MDPI and Wiley publications. So, as you see, she is a specialist. She has thesis on membrane separation, membrane-based separation, really on the gas separation. So it's a very good opportunity for all of us to learn from Dr. Rajashree Borgohain about this subject today on the bio-based membranes for carbon dioxide separation. So let me invite Dr. Rajashree to give a talk on this subject today.
Good morning, everyone. I am Rajashree Borgohain, and today I am going to speak about the bio-based membranes for CO2 separation. And this work was done under the guidance of Professor Vishnupada Mandal in the Department of Chemical Engineering, Indian Institute of Technology, Guwahati. Before going to the topic, I would like to share some of my institute's picture. Indian Institute of Technology, Guwahati, is situated in the northeastern part of Assam, which is and India. And this institute is the sixth member of IIT fraternity, and separation science laboratory situated in chemical engineering department was my laboratory, and Professor Vishnupada Mandal was our supervisor, and I have included his profile as well. You can go through his profile. In our laboratory, generally we work on carbon dioxide capture using membranes, absorption, adsorption, and some works are going on for fuel cell membranes, and also some other kind of water purification treatments. Okay, now we are going to our topic. So we all know that carbon dioxide is increasing in the atmosphere day by day, and it is the main reason of global warming. Now, one point is from where this carbon dioxide is coming. There are many sources like transport, residential, non-residential industries, and some in energy industries, some electricity and heat production plants. And these electricity and heat production plants are the main sources of carbon dioxide. And also one more point, that the upper safety limit of carbon dioxide in the atmosphere is 350 ppm, which is already crossed, and it has already reached 421 ppm from the data obtained for March 2023. That means carbon dioxide is increasing gradually in the atmosphere, and if it is not mitigated on time, then it may create some more problems in the near future. But if there is a problem, then definitely there are solutions too. So there are main solutions like reduction of energy intensity. Here we can reduce our use of energy, which is not very possible, and then reduction of carbon intensity by using some renewable resources like nuclear energy, then wind energy, hydro energy, or solar energy. Then one more is the carbon capture and sequestration. My work is based on this carbon capture and sequestration. These carbon dioxide capture technologies can be divided into absorption, adsorption, cryogenic distillation, and membrane-based separation. I have chosen membrane-based separation due to its low cost, easy to handle in nature, and also it is very corrosion-free in nature. These membranes again can be divided into three types: ceramic, polymeric, and mixed matrix membranes. This ceramic membranes has the thermal and chemical stability, but it has the high fabrication cost, and also it is very brittle to handle. Then the polymeric membranes is economical for fabrication, but it has high swelling, which reduces the selectivity of the membrane, but the advantage is it increases the permeability of the membrane. Then comes the mixed matrix membrane. It is the combination of both ceramic and polymeric membranes. Here, polymers are the main base of the membrane, and then fillers helps to enhance the membrane performance. That means this membrane has the advantage of both ceramic and polymeric membrane. I am working on this mixed matrix membrane. It is very robust to handle, and also it has moderate cost for fabrication. Now, how these membranes work? There are mainly two mechanisms. One is solution diffusion and one is facilitated transport. In solution diffusion, the gas molecules get adsorbed on the membrane surface, then it travels through the membrane, diffuses through the membrane, and then it gets dissolved in the other side of the membrane. It is a very simple process. Then comes the facilitated transport mechanism. Here, the membrane requires some filler, carrier. Here, the gas molecule, that means carbon dioxide gas, is carried by some carriers, which can be a fixed carrier or can be a mobile carrier. So, an example of a fixed carrier is a chitosan. Here in the structure of chitosan, we can see that the NH2 group is there in the structure. This is a one site for CO2 carrier. And mobile carrier is piperazine, ethylamine. So here the difference is fixed carrier is a long chain carrier and mobile long chain carrier, and that means some polymers can be said as the fixed carriers, and the mobile, it cannot move through the membrane, and the mobile carriers are the mobile materials. That means the piperazine very small amine, ethylamine small amine, so these can be the mobile carrier. And generally what happens, the carbon dioxide reacts with the amine and it forms a zwitter ion, which is very unstable. Then this zwitter ion, in the presence of water, it forms a bicarbonate, which helps in the transport of the carbon dioxide throughout the membrane. For my work, I have chosen chitosan, a derivative of chitosan. Why I have chosen a derivative of chitosan? Why not chitosan? Let me explain. Chitosan was experimented for at room temperature by Eto et al. They found that the carbon dioxide permeance is 36 CPU and selectivity is 70. But we need to check it at higher temperature also. So that was done by El Azami's group, and they found that the carbon dioxide permeance is 7.4 at higher temperature, and the selectivity is also 43. But here they have used a higher thickness than Eto et al. After that, we have found one more literature for chitosan and Quebecs. So there also this work was also done at 85 degrees Celsius. Here also the carbon dioxide permeance is 68, selectivity is 65.3. It is quite good. Then another work was done by Prasad et al. Then it was done at 90 degrees Celsius, and the CO2 permeance was found as 24.7, but the selectivity is higher than the previous one, like 80. Similarly, when polyallyl amine was added to the chitosan, it was found that the selectivity is increasing to 60. But in all these cases, they have mentioned that they were using chitosan in a acidic solution. Whenever they are adding some amine to the solution, there was some precipitation, and this precipitation hinders the gas molecules to pass through, and also some kind of unreacted chitosan present in the system, so which is also a hindrance for the gas molecules to pass through. So another work was done using carboxymethyl chitosan, which is a water-soluble derivative. In this case, there is no need of addition, no need to add some acid to make the solution. So this is a water-soluble chitosan. And Sen et al. Was performing this experiment at room temperature, and they found that CO2 permeance as 0.36 CPU and selectivity as 33. Other than this work, there was very limited work available using carboxymethyl chitosan. So I was working on this by varying the temperature, pressure, and also some moisture flow rate, temperature, like that. So then let's discuss about that, what I got and what are the challenges I found in this case. But here one important thing is carboxymethyl chitosan forms a membrane, very smooth membrane, and more than the chitosan membrane, it forms a smooth membrane. So that means this membrane is a potential membrane for carbon dioxide capture. So let me talk about the experiment. In this case, I was using the polymer matrix as carboxymethyl chitosan, as I told already. Then the carrier I was adding as piperazine, a small molecule amine, then polyamide amine, which is a large molecule amine, and some fillers I was adding. That was one was carbon nanotube, then another one is hydrotalcite. Here, the polyamide and the piperazine will help in facilitated transport of the gas molecule, and then these fillers will help in forming the alternate paths for the gas molecule. Now, The carboxymethyl chitosan was synthesized with the help of chitosan uh, by treating it with sodium hydroxide and monochloroacetic acid. And this material has excellent film forming ability, good water holding capacity, and the degree of substitution we got as 75.84 percentage, and a viscosity average molecular weight we obtained as 3.54 into 10 to the power 3 kilodalton, and then it was confirmed by HNMR, and we verified it with the available literature as well. And this carboxymethyl chitosan was used to prepare the membrane in the future. Now, how these membranes are prepared? Water we took as a solvent, then carboxymethyl chitosan was added to the solution, and it was stirred at room temperature for 8 hours. After that, filler was added to the system, and with the help of sonation, the filler was dispersed properly in the system, and also amine was added dropwise later. And we perform centrifuge in case if there is some kind of bubble formed during the reaction. So we got a smooth mixture, and this mixture, to cast this mixture, we use the polyether sulfone support, which has a pore diameter of 0.1 micrometer. This is the FSM image of the polyether sulfone support that I used for the casting. And it was pasted on a glass plate, and then it was fixed properly. The polyether sulfone support was fixed properly. On top of that, the material that the solution I prepared was poured and then casted with the help of the doctor's blade. Now this membrane was then dried at room temperature for 6 hours, and then it was put inside the oven at 110 degrees Celsius, so that the remaining water vapor can goes out, and we will get a dry membrane, which has the uh, thickness of approximately 1 micrometer. And here we can see that this is the active layer. That means this is the part that I have cast on top of the polyether sulfone support. This porous part is the polyether sulfone, and this part is the active layer, that means carboxymethyl chitosan, and this is the top surface of the membrane. And here we can see that there is no defect on the membrane, uh, because defect-free membrane is very important for gas separation performance. So after that, this membrane was cut into a circular piece, and it was fitted inside a stainless steel module, which was then placed inside a hot air oven, so that we can change the temperature for our experiment. Initially, the carbon dioxide and nitrogen gas mixture was sent to the system with the help of a mass flow controller. Here we are using 20% of carbon dioxide and 80% of nitrogen. Then we are using argon gas, which is so that it can act as a sweep gas. After reaching the feed gas to the system, one part will be the permeate. That means the membrane will separate the carbon dioxide and nitrogen gas. Whatever will be permeated, that will be the permeate gas, and whatever will remain in the other side of the membrane, that is the retented gas. Both gas streams are then sent to the gas chromatography, so that we can get the result of retented and permeate gas. After that, with the help of some calculation, we obtain the CO2 permeance, nitrogen permeance, and then the CO2 nitrogen selectivity. In the whole system, we were supplying some water, some amount of water, calculated amount of water, to the both feed gas and the sweep gas. So this water was then again dehumidified with the and was taken out before sending to the GC, and it will be collected through the water knockout. After that, we got some results for like that. like for only carboxymethyl chitosan, the pristine carboxymethyl chitosan, it showed the result as 35 GPU CO2 permeance, and then CO2 into selectivity as 39 at 80 degrees Celsius, and sweep feed water flow ratio was 1.67. This is the highest result it was showing. And then already we have seen some result of pure chitosan material. It was showing at the same temperature and same feed sweep water flow ratio was 12.5 GPU, and the CO2 N2 selectivity was 54. In this case, we can see that the CO2 permeance is quite higher than the chitosan, but the selectivity is less. So that means this carboxymethyl chitosan membrane is it can be a good CO2 separation membrane if we increase its selectivity, because already we come to know that its permeance is good, but selectivity is a bit less than the chitosan membrane. So if we work on the selectivity part, then it can be a good membrane for CO2 separation. And also we found that this membrane is thermally stable up to 274 degrees Celsius, and also it has some high moisture retention ability. So after that, we have added piperazine to the carboxymethyl chitosan membranes. That means piperazine is a small molecule amine, and this amine can act as a CO2 carrier, a mobile carrier. As we already discussed that this CO2 can be carried by fixed carrier or mobile carrier. So here the piperazine will act as the mobile carrier. So we have changed use so many percentages like 10%, 20%, 30% piperazine for our work, and we found that 20% piperazine containing membrane gave the optimum CO2 separation, which was 72 GPU CO2 permeance, and the selectivity was 102, which is far better than the carboxymethyl chitosan membrane. But in this case, what we found that the long-term stability is very less. The membrane was stable up to 3 days. After that, the result was started decreasing. And this was because the leaching out of the amine molecules from the membrane. So to overcome this problem, we used another amine, which was a large molecule amine, polyamido amine. And this amine was again varied with the percentage 10%, 20%, 30%, 5% like that. So from here also we obtained that the 10% polyamide amine containing membrane showed the optimum CO2 separation, and it was stable more than 100 hours, more than 10 days. And so here we can see that at 80 degrees Celsius, that means at the same temperature and swift feed flow ratio uh, as the piperazine containing membrane, it was showing the CO2 permeance as 83 GPU, and the CO2 N2 selectivity was 124. That means it was showing the good permeance as well as good selectivity compared to the piperazine containing membrane, and also its stability was good. But when we increase the temperature to 90 degree and we increase the sweep feed flow ratio, then we found that it was giving far better than the at the membrane at 80 degrees Celsius, and also the sweep feed flow ratio 1.67. So that means the membrane, the optimum condition for this polyamide amine membrane at 10% polyamide amine membrane is at 90 degree, and sweep feed water flow ratio is 2.33. So after that, we have added some fillers. One filler is carbon nanotube. It has the tube-like structure, and this was carbon nanotube was initially wrapped with CMC itself, and then it was added to the CMC solution, and we formed the membrane. Here also we found that 1% CNT containing membrane was showing optimum CO2 separation. weight, one weight person. Here I am talking. So here also we can see that when CMC was showing 35 GPU of CO2 permeance, CNT was showing only 43. That means not a very good improvement when we are adding CNT. And also selectivity was also 39 and 45. There is not much difference. So that means CNT is not very good filler for this CMC membrane. So we have checked with another material, which is hydrotelsite. It has a sheet-like structure, and this using this hydrotelsite, we found that this membrane was showing a CO2 permeance of 70 GPU and CO2 and selectivity of 13. Here also we can see that CO2 permeance is good, but the CO2 and selectivity is not very good as compared to the pristine CMC. So here we can see one more point, that when we have added sweep feed water flow ratio 2.33, then only it showed the optimum result, and also the temperature was 80 degrees Celsius. The same sweep feed water flow ratio was used for polyamide itself when we previously, as we discussed here, 2.33, it got the optimum result for CO2 permeance and CO2 endoselectivity. The same feed water flow rate was used here also. But this membrane was also stable more than 100 hours. So we decided to add both polyamide and this hydrotelsite together. So after that, we got a result like at CO2 permeance of 123 GPU, and the selectivity was also 67 at the temperature of 90 degree. So finally, we concluded that among all the experiments, this CMC polyamide and hydrotelsite membrane was the best membrane among I have tested whatever the membranes was there. The pristine membrane, then CMC piperazine, then CMC polyamide, and CMC CNT, CMC ST, and then finally the CMC polyamide and ST membrane was the best membrane for our work. But during this limited time, we have performed these experiments. So we haven't checked about other combinations also, but we can check other combinations later. So from all those work, we can conclude that this membrane was thermally stable for performance, and these membranes are moisture responsive in nature, and also it can form some defect-free thin layers over the support, and this can be a very good membrane for CO2 and separation as well. These are some references that I was used for this work, and thank you for your attention. And if there is any question, I am ready to answer.
Thank you very much, Dr. Rajashree. Very informative presentation on the bio-based membranes for carbon dioxide separation. Guys, now it is open for question and answer session. Feel free to post your questions in the question box. So Dr. Rajashree will address them appropriately in the session now. So feel free to post now. Rajashree, I'm going to show you the questions onto the screen and you address them appropriately. Yeah?
Yes. Yes. What are the challenges to prepare a membrane? Yes. Actually, this is very important for anyone who is preparing a membrane. The first point is it should be defect-free. To make it defect free, we need to remove the unreacted particles from the solution. Here we used centrifuge to do that, and then to minimize the these unreacted particles in the solution, we can do some a longer time of stirring also we can do, but it will depend how, what is the polymer you are using, and also what is the material you are using. Some cases we can use sonication also, so that it can give a proper dispersion. And this is the main challenge, because when I started this work, then we were we are not getting very proper membrane. Some defects like holes are coming, so we need to be very precise, very clean. The place where we are casting the membrane, the area should be very clean, the environment should be very clean. And after that, while drying also, we need to take care if there is any particles coming from outside. So we were using laminar flow hood also, instead of keeping it outside. And then while keeping in the oven also, we need to take care that other materials are not inside the membrane, otherwise it may create some other problems also. So we need to these are the main challenges, like small problems, but it may create a bigger problem for fabrication of membrane. Yes. Yes. What is the role of moisture in the gas separation by membranes? Yes. Uh, Actually, moisture plays the main role in the membrane separation, in this gas separation, because carbon dioxide is reacting with amine in the presence of moisture, in the presence of water. That means the reversible reaction, which helps in the facilitated transport mechanism, was played by the moisture only. And also this moisture helps in making flexible, giving flexibility to the membrane. And that is one more point, because if a membrane is flexible, then the permeability will be higher. And also there is one more point, like if we are adding giving like at the higher temperature, the membrane, otherwise a membrane can be a brittle membrane. If we are supplying moisture, it will help uh, to maintain the membrane structure. Yes. Key process parameters involved in membrane-based gas separation. Uh, the main parameters are for pressure, temperature. At room temperature also we can do gas separation, but pressure we need to apply. And then temperature we are using, because the flue gas comes at 59 degrees Celsius when it is coming as with nitrogen. So at the higher temperature also, the membrane should work for this gas separation. And the pressure sustainability is also important, so that it can be used for this natural gas purification, because CO2 CH4 mixture, if we are going to separate that system, then we need to take care that it must sustain some pressure also, because the natural gas contains higher pressure. So that are the main parameters. What are the important points that we need to take care while doing the gas permeation experiment? Actually, this is very important, because I'm happy to answer this, because when we started doing this experiment, uh, initially the temperature, maintenance of the temperature, like if we are having a it should be a proper oven while to maintain a temperature, and we shouldn't interfere while it is the experiment is going on. Then one more point, the supplying of the gas. So the regulation. So we need to give a proper flow rate to the feed gas and also to the sweep gas, because the sweep gas flow rate should be lesser than the feed gas flow rate. Otherwise, there won't be a concentration pressure gradient, and it will disturb the it will hinder the flow gas transport. And also one more thing, the main point is there should not be leakage in the pipes. The stainless steel pipes we used to use, but in those cases also sometimes some leakages come, and this leakage, uh, we should take care of this leakage also with the help of some soap bubble and or water. We need to check whether there is leakage in any point. If any point there is a leakage, then it won't work, the whole system won't work. So that is one more point. And also that's while we are supplying the moisture also, this should be a distilled water. It should not be some contaminated water also. That will also uh, create some problems inside the pipes also, because it may create some corrosion, and sometimes some particles will be stored inside the pipes and it will clog the system. These problems are generally we faced, and while after when we overcome these problems, then only we got a proper results. Yes. Is carboxymethyl chitosan the best membrane among all the membranes used for carbon dioxide separation? Yes, that is very important also. Definitely not. Carboxymethyl chitosan membrane is not the best membrane among all the membranes used for carbon dioxide separation, because there are various membranes like for synthetic membranes are there. So synthetic membranes are giving good results also. Polyimide membranes are there, and but this is the bio-based membrane, and already I said that there are very less works using this carboxymethyl chitosan membrane. uh, I think after one work by Sen et al, I was using this carboxymethyl chitosan membrane, and I explored some probabilities. After that, I found one more literature recently, few days ago. It was done by Lee, and it's their Lee's group, and they found the CO2 permeance as 1278 GPU, which is very good CO2 permeance. And also they were adding some kind of polyimide inside the carboxymethyl chitosan, and also octopus-like structure, nanostructure. That is also a good result for carboxymethyl chitosan. But yes, we can say that it has probability, it has potentiality to be a best membrane in the future, if we work on this in the future also. What else gases can be separated by membranes? Yes, actually by membranes means if it is carboxymethyl chitosan membrane, then it can separate now carbon dioxide, because it has the group NH2 group, that means a amine group is there, so it is very CO2 selective in nature. It is CO2 selective, so we are using for that. But for oxygen also we can try, and most importantly, SOx and NOx gas separation should be tried with the help of the membranes, because it is also present in the flue gas system. So if this membrane can sustain these systems, SOx and NOx gases, then definitely these membranes are very good for these flue gas separation systems. Yes. any information on commercial applications, particularly on membrane suppliers. There are various membrane suppliers but for these membranes, whatever I am using, that the membrane supplier is not available, and commercial application, if we say about commercial application, very less applications are there, and it is not properly used in industries currently, but people are trying in Ohio State University for the pilot scale development using polymeric membranes, mixed matrix membrane basically for carbon dioxide separation. But yes, there are so many commercial membranes which are used for water purification, but gas separation there it is not available as far I know. Cellulose acetate, some people were used, but it is not widely used. Yes, one more point here I want to add. The particularly one membrane supplier we were in touch, the Starlitech. From them, we were using this polyether sulfone supports. That was also a membrane, porous membrane. So we were purchasing that membrane from that company supplier. Yes. Yes, can carboxymethyl chitosan membrane sustain high pressure? Yes, it can sustain up to 40 bar pressure, and beyond it, I didn't experiment it, but maybe it can sustain.
Hey, that's all the questions we have, Dr. Rajashree. Thank you very much for doing a wonderful presentation and also addressing all the questions. Before we end this session, would you like to give final remarks to the audience?
Yes, thank you so much for your attention, and special thanks to TechnoBiz, because I got this opportunity to present and talk about bio-based membranes for carbon dioxide separation. And although I was concentrating only on carboxymethyl chitosan, but there are so many bio-based membranes. But yes, yeah. And thank you so much, everyone who are present, who are live and listening to my talk. And if you have any other question that I haven't answered, and also if any question in my presentation also, please write to me, and I have given my email address in my last slide also. That is borgohain@gmail.com. And yes, thank you so much. And I'm sure that we will meet again.
Thank you, Rajashree. Excellent presentation. And guys, that's the end of the session today on the bio-based membranes for carbon dioxide separation by Dr. Rajashree Borgohain. And she requested and suggested, if you have more questions, feel free to reach out to her. And as you know, she specializes on this gas separation by using the membranes. That's the end of the session today. I'm hoping to see you in the future episodes of the Membrane Filtration Tech Talk. Thank you all. Bye-bye for now.